Click the bell icon to get latest videos from Ekeeda.
Hello friends, today we will talk about the choice of evaluation plans. That means after the query has been transformed and been optimized, then which evaluation plan which will fit to the execution engine so that we can have the minimum cost onto this evaluation. So we will talk about this choice between the join orderings, the complex joins, the natural joins, and many other forms like the heuristic database, the nested loop joins, the particular on the plan caching, and every time of this meosing on these ratios. Now we will talk about the description on this evaluation plan rather than concentrating on the query optimization. The choice of evaluation plan happens after the stage of query processing and transformation. Whenever a query is processed or transformed, then we find the equivalent transformed query of many of the relational algebra expression. Now, each of this expression has an evaluation plan executed with it. We have already described that how to generate an evaluation plan with an associated relational algebra expression. After the expression that we have generated, the evaluation plan need to be optimized on best of a query that which is the least cost effective one. Now the least cost one we will take and fit to the execution engine to get the query translated and calculated on a database and give back the result by this query by example engine or QBE. Now, whenever we perform this type of task, the first one is to generate all the possible expression that we can have from a particular query and then generate the evaluation plan associated to it. But the cost of generating every possible equivalent expression will be enough for not having an optimized query based organization because it can be lies there a lot number of options for the expressions for the evaluation plan that we are generating, so it will cost around a lakhs on number because the cost of the optimization now will be a problem for the optimized query. Let us look at this example. Now, if we are talking about the join order on the cost based on evaluation, say suppose we have R1 through Rn number of relation that we need to join within a where clause or within a natural join clause. Now, after we are joining, if n is the number that we are concerned about, then we can have this much different join orders. So now we can see that we are having 2 into n minus 1 factorial divided by n minus 1 factorial number of join orders. Say for an instance, if n is equals to 3, for n is equals to 3, we can have 2 into 3 minus 1 or 2 4 factorial divided by 2 factorial. So that means we are having only 12 possible join orderings out of these three relations. But with this 5, we will have at least 1680. With this 7, we will have 665280. And with 10, it will go till 14.7 billion entries. So see that only a 2 number of increase or 3 number of increase in n will actually having a thousand number of increase in the join ordering. That means R1 with R2 or R2 with R1. So we need to consider this join order very carefully. Otherwise, we need to consider all of this expression that is not desirable. Because if we are generating 14.7 billion expression for a relation that is 10 relations, join them, then it is impossible to reach an optimized query based on a cost. Because when we are taking a cost based optimization, then we need to calculate the cost of every evaluation plan that is associated with an expression. So it is not possible for us to generate 14.7 billion cost for an evaluation plan and then compute them, that which is the least one. Now we have to choose some probability and acceptance on this joint ordering. Now how we can achieve that? Let us first take three of this relation and then see that what are the joint orderings that we can have on them. So with the R1, R2 and R3, we can have R1 joined with R2 and R3. We can have R1 joined with R3 and R2. Again, we have R2 and R3 joined with R1. And finally, R3 and R2 joined with R1. So we can see for R1 alone, we can have four types of joint orderings. Same with the R2, same with this R3. Now for R3 also, we will have a set of this one, that this is the last 4 on this 12. So the R3 will go for the R1 with R2. And finally R2 joins R1. Now we can see that if we are having this comparisons of R1, R2, R3 that has generated 12 different possibilities. Now if we perform Now for this 3, we have already 12 orders, and if we want to join this with as 1, 2 and 3, that means if we consider this as relation 1, this with relation 2 and 3, then we will have again 12. So for each of this one, we will have 12 join orders. Thus we will need 12 into 12, that is 144 join orders for joining R1, R2, R3, R4 and R5. But rather, if we take it as a set of R1, R2, R3, and if we have R4 and R5, then the same joining can be listed as with this 12 and 12, that means 24. So which is less than 1/3 of this particular join entries on a join ordering. So this is the way we need to select on a dynamic programming, that based on the data or the relation that is coming up to us, if it is less dense or concentrated, then we can choose as the set-wise joining other than the natural joining of each of the sets together to have the less number of join orders. Now we can generate the 24 number of join orders and the evaluation plan associated to them rather than generating 144 evaluation plan. So thus it will less make a comparative for taking us this dynamic program where we can generate each of these plans according to the associated set. Now we can generate the dynamic program for this optimization on an evaluation plan that we can generate from each of this associated set. Let us describe that how we can achieve that from 144 to 24, or rather than a 1/3 or 1/4 number of entries for a number of n relations. Say that for a query of S, we are introducing a procedure that is the find best plan procedure, which will in turn generate the find best evaluation plan out of the query S. Now we first take an array of best plan and then initiate it with an infinity. Now, infinity means there are infinite number of possible on the best plans that we need to calculate each of these best plans and then put it into the best plan array. Now, the best plan S will consist of one best plan. After that, we have calculated this program. So for the initial, it is equals to infinity. Now, if it is not equals to infinity, then we are mentioning that we have already optimized the best plan. Now, if our query is regarding only with one relation, then what we need to do? Now, if it is relation belonging to only one, that is the S is containing, that means there is no need to join order perform on this S. Now we can have the best way to find the cost on S and display that as a base plan on S. Now we have stated that the best plans and cost are the best that to be sent. Now what happens that if S is containing more than one relation? Now for each of the subset, that is S1 for this belonging to S, that means the S1 is in subset of S and that is not equals to S. That means the subset cannot be equals to this S. So now we need to perform this query evaluation engine to take up the evaluation plan and generate the best plan. Now see what we are doing. We are finding the best plan for S1 and also the rest of S1 so that we can compare between these two, that which is the cost that is the least 10 and the best effective one. Now that we have computed A, that is the best joining result between P1 and P2. That means the S1 and the rest of this S, we are joining based on the condition that it is the best joining order and we have generated this as A. Now we need to calculate the CAS. Now for the cost of this S, we are taking the P1's cost, the P2's cost, also the cost of this joining. Now we need to check that which of this one has the least. Now if my cost that we have calculated, that is cost of P1, cost of P2 and the cost of A, now we need to check that is the cost is less than the best plan S's cost or not. That the previously calculated cost on this particular S, and if it is less than the cost of the now calculation, then we will take the cost as now of the best plan's cost. Now what will be my plan for execution? We have to need to first execute P1, then P2 and then the join ordering. In this way that will be my best plan and the cost will be my best plan's cost. So now we are having that execution of the P1 plan, P2 plan and finally joining them using the A. So now my best plan S is consisting of the best plan. We need to return it to the result. Now that we have taken the joint ordering of P1 and P2, so for what reason we are having that we can have the possible best join orderings among them? As we have seen that for 5 joinings as a set of 3 and as a set of 2, we are having only 24 if the join orderings are performed at right. that the set is mentioned in a distributed order. So in which order we should choose the joining? Say for an example, if we have the joining of R1, R2, R3 with join R4 and R5. Now, if this joining on this R1, R2, R3 and R4, R5 has the common attributes from R4 and R5, then we can say that the join is of a particular interesting sort order. So what do you mean by an interesting sort order? That it can be met on the sort order useful to that particular joining. Now, if we made on this joining, then we can say that the R4 and R5 is the common attribute. Then actually the join relation is having on the right operand and the joining relation is having on the left operand. So if some common attributes belong to this R4, R5, then it is based on the joining R4, R5 will be useful to us. But if the common attribute is of R1 and R2, or R2 or R3 or R1, then we can say it is not becomes useful, because now as the joining relation we already have the R1, R2, R3 attributes. We do not need to repeat that attribute as the common attribute or for the join relation, because now the joined relation is R4, R5, not anymore this R1, R2, R3. So in this way we can introduce the interesting sort order so that we can shorten down the actual number of join orderings. And we have to check for each evaluation plan that which are the sort ordering that we are taken considering. If it is particularly of an interesting sort order, then we can take that for consideration. Other than we can skip it if it is taken for an cost-based optimization. Now, when we talk about the equivalence rule, that means we are talking about a physical equivalence rule. The physical equivalence rule means we need to generate all the possible relational algebra expressions, not the evaluation plan, but the relational algebra expression from which we can take out some of this expression if they seem to be more approaching than the other one. And we can generate the evaluation plan based on that expression. So till now we have considered the join order cost optimization. Now we are talking about the equivalence rule optimization. So for the equivalence rule, we need to generate the equivalent expressions according to the equivalence rules that we have described previously. Now we are more into the cost of that particular equivalent rules. So the steps are, first we need to express or generate the expressions. Second, with the dynamic memoization. What do you mean by memoization? That means we are having some expression that can be generated from a previous expression with some modifications to it. So this physical rules that is considered to be the dynamic memoization can be our option to calculate the best cost effective or the least cost plan out of this generated expressions. Now, how can we apply heuristics on this search? Now, some heuristics rules are the selection and the projection rule. What do you mean by in selection rule? In the selection rule, that we need to make all the selections as early as possible. That means when we are selecting some operations on an expression, that means we are selecting some attribute out of the relation. So the selecting attributes means we are selecting on a performed condition or a predicate on the attribute values. So if we are adding these attribute values to the relation, then we can say that out of every relation, we are having only a part of the tuples from belonging to the relation, so that we are shortening down the relation so that the next join orders on this relation can be performed very easily. Let us look at this query. See, if we are having this expression that pi name title goes with the name department, that is instructor join teachers, and the selection CID C01 on this course relation. Now the first one that we are fetching as an input operation is this CID that is equals to C01. So we need to perform that. We are selecting some predicates, that is, if the course ID equals to C01, only that tuples to the relation that is being joined to instructor join teachers. Now we can more just elaborate this query by reforming it with more of the selections, and we need to put the selection operation as early as possible. Now this query will give us that we are performing the D percentile on name selection, that is whose instructor's name starting with D. So now we can have these selections on the instructor relation only, not the joining of instructor and teachers relation. Now see what is the difference here. First, in this query, we are joining the instructor and teachers both and then having the result as our final or intermediate query. Now we are performing the projection name and department from that instructor join teachers. In the second one, we are having the selection on the instructor relation only. So now only the tuples that belongs with the name starting with D can be joined with teachers, thus generating a much shorter relation as an intermediate result. Thus joining with isn't course ID equals to C01. So we can see that as early we can make the selections as it is possible to give us the better query or an evaluation plan that can be generated from it. As we know, there are more options to generate evaluations plans of a particular expression. So if the expression is built up properly, then the evaluation plan can be generated very easily. Now the join ordering that teachers join instructor on this name instructor basis, or the instructor join teachers, or the whole selection is made on a joining. So the innermost part, if we have the selection operation, then it will give us the best possible evaluation plan. The next one is to project early. That means to introduce the projection early. What do you mean the projection? That means we are selecting only a number of attributes out of the relation. The selection gives us the number of tuples, whereas the projection gives us the number of attributes. Now, if we put this projection operations as early, that means we are again shortening the relation by the number of attributes, but not the number of tuples. Now, the difference between projection and selection operation is that the selection, if there are much more entries associated to each of the relation, is becoming useful. Whereas if we are having a much more attributes that is associated with a particular relation, projection is helpful. So now we will see that how projection will help us. Now look at this query that we are having the joining on the instructor, teachers and courses, and finally selecting the name and title and projecting them as a result. So now we are having all the attributes from instructor, teachers as well as courses as the joint result, and it will incur an extra overhead of having all the attributes where we will need only the name of the instructor and the title of the courses that he is teaching. So it is obviously not desirable to introduce this much expression because it can generate a number of evaluation plans based on the condition that the join orderings are many type possible, and also there are many attributes according to which the cost can be calculated. Now if we can project a number of tuples or an attributes out of this one, then it will be easier for us to create the evaluation plans. Now, if we perform this query, that we are selecting at first the course, the CID and title. So from the course relation, we will have all the course ID and associated title with it. Now, so to join that with teachers, we are having the common attribute CID and also the name of the instructor that is teaching that particular course ID. So now we are having from the teachers the name and CID, joining that with all the instructor fields or attributes, and then selecting from that name and title of the particular instructor, the teachers from the course ID, and from the course the title of that particular course. So in this type of expression where we are projecting early, that means we are shortening down the relation as much as possible. Now, as a combination of a selection and projection, we can achieve the best evaluation plan or the best expression from which the best evaluation plan can be generated. Now, if we consider this one and we can generate this query, so what will happen here? We will first select all the course IDs, the C01 with the course, and then from that we will select the name and CID of the teachers, and after that we will join that with an instructor whose name starts with D. So now we are having the best one because we are using the selection, the projection as early as possible from the relation where we are selecting the name and title from the resultant relation. So it is absolutely important for us to go for the heuristic, that for each of this evaluation plan, which is the heuristic that we are using, either the selection early or the projection early. Now more of the possible and this successful heuristic optimizer uses the R optimizer. What do you mean by an R optimizer? Till now what we are doing is a non-left deep root join ordering. But if we produce a left deep root join ordering, that means on the right operand of each of the joining, we will have a relation, not another performance on the operands. So now directly we are having a join ordering on a relation and with another joining or another relation. So the right operand, if it is confirmed with a relation, that means we are directly fetching the relation as the joined part, not any other joining. So now we can achieve a better depth on this left deep root joining, where the depth one and the width one is our best concern. Now let us perform an R1 to R5 joining with a left deep root and also a non-left deep root joining. Now if we have R1 and R2 as the best one, then we are having the join on R1, R2. Now with this join, we can have only a relation that is being joined as a right one. Now with this R1, R2 join R3, we can have other join that is also a relation on the right one. And finally, with this join, we can have R5 as the final one to join. So we can see that all the right hand operations are growing as the relations, not another joining or not any other portions on the selection and projection. With the R optimizer, we can achieve this with now on this right hand side of this outer join, we are having the join on R4 and R5. It is not the direct join from the relation to the join. It is a join operation that is being joined with another join. So this is a non-left root join and this is a left deep root join. Now what is the difference between these two? In the left deep root join, we can have only the big O of n factorial number of orders that is possible. That is a much lesser one where we can have in this non-left root join as an n of 2 to the power n to the power n number of joining that we have already seen. Now for the R optimizer, we can have big O of 3 to the power n because here we are considering 3 as a basis on the relation. So we can see the difference between these three as this O n factorial as the best one to choose among them because this will give us the minimum possible join orders out of which we can choose. So the along selection and projection, also this deep root joining or matters for a selection on the evaluation plan. Now after the optimization cost budget, we need to consider for a particular scenario. Say for an example, an university needs to provide a particular query that is being a heuristic part. That means it will search for the course every time some university student is inquiring about the course, but every time within different student ID. So if the input of a particular relation changes with the constant value every time that query is performing, then we need to perform plan caching on it. So what do you mean by a plan caching? That will cache a particular situation and then change the constant value. Say for example here the student ID. It is the constant to the query that every time only it will be changed and the course information the university will generate. So now my plan caching is dependent not only the attribute but also the value of that attribute. So further we have considered all the join orders, the heuristic searches, the selection projection, the plan caching, and also the deep root joining on the left and non-left. Now we will talk about the nested joins on a particular query that we will consider the cost optimization. Now, if the outer query based on the output on an inner query, where the relation of this outer query and the inner query matches with each other, then we say that the variables are correlation variables, where the variables from the outer query is used in the inner query as a part. That means we need to store somewhere the outer query's variable so we can use that as an inner query, because the inner query is the most innest one that we can available with the query optimization engine. So let us see how to perform this one. Now let us look at this query that we are fetching an instructor who has been teaching some courses on the year 2007. Now that we are selecting the name from the instructor where exists the select star from the teacher's relation where the instructor ID and the teacher's ID matches and also the teacher's year equals to 2007. Now we can see that we are having the teacher's year equals to 2007. This one is fine for this inner query, but we have in correlation variables that is from the instructor, we are getting the instructor ID. Now the instructor ID and the teacher's ID, if matches with each other, then we are selecting the tuples from the teacher's relation. So what we are having a correlation evaluation. Now this type of correlation evaluation is not absolutely important and desirable for us, because we need to store the instructor and their IDs for each of these inner queries and associated to that for outer queries. That means for each of the tuples in instructor, say for the instructor has 3 tuples, so the 3 tuples will go with all the values on the tuples of the teachers, the second also the values with the teachers, the third also the values with the teachers. So in this way we are having that for this 3, if there are 5 tuples in the teachers relation that matches with the 2007 condition, so there will be 3 into 5, 15 tuples, which is not really necessary. Now we can generate that from this correlated evaluation either using this join ordering or using the cost optimization based on this nested queries. So when we are using nested queries, that means the inner query's result will be a part of this outer query. Now we are using this where exist condition. So the where exist condition suggests that the instructor ID's tuple must belong to this one that belongs with this teacher's relation. So how can we this one? Say suppose we are deriving the query again in this manner. Now if we rewrite this query as this one, so we can have that the select statement on now is being used the joining on the instructor and teachers, not the instructor that exists with the relation teachers. Now it has one advantage and one disadvantage. The advantage is now we no need to perform the correlated evaluation. We can have just join the instructed teachers, and from that we can select the teachers equals to 2007. Now my instructor and teachers will be joined with the condition that the ID is the common attribute. Now one advantage is that no need to select the correlated evaluation, as I have already told, that here I can use the teachers relation. From that we are selecting the instructor, where inside these teachers we need to match the instructor teachers. Now within this condition we are just performing the joining. But the second, that is the disadvantage of the second one, is that we first need to join all the tuples from the relation instructor and teachers, and now from that we are selecting the name based on the condition teachers are year equals to 2007. So we are not projecting something here, we are directly selecting over some joining. So here it will produce a larger relation comparative to this one, but it will be most cost effective comparative to this one, because now we are not having the correlated evaluation, which in turns produce a larger cost optimization. So if we are having instructor and teachers, and sin 3 into 3, that we will have only the 9 number of tuples instead of 15. So we are actually shortening down the relation. Now, like the previous example, it is not always possible to move the nested query or the subquery into just a query with a join relation. If we have this query inside a format that use a particular temporary relation, which uses in fact a relation that cannot be just joined with the previous relation, then we need to perform the nested subquery cost optimization in a different way. First, let us look at this syntax. So now we are having the joining in that way that the outer query is to select some attributes over some relation with the predicate 1. Now the predicate 1 is also companioning with another relation that is joining within the condition of predicate 2. So now not only it is belonging from some relation that is a correlated evaluation, but also we are having some predicates to perform with this correlation evaluation to have the actual results from L1. Now what we can do, we can divide it into two temporary relation and then have the result from it. Now we are creating a temporary relational table T1 to select a distinct V, that means the distinct attribute from L2 that we are selecting here. Now we are using P21. What is this P21 suggesting? That the P2 without any correlation variables. So now we are not considering the correlation variables that we are having from L1 and L2. Just we are having the L2, selecting the distinct value for the attributes, and now we are having the predicates P2 over them. Now we can create the outer one with the correlation variables. Now we can have that we are selecting some attributes over the relation L1 and T1, where we can have P1 and reintroducing the predicate P2 with 2, that means with the correlation variables. See, here we are considering without the correlation variables, that is only the L2 and the V. Now we are using the table as a part of this joining, where we can using the predicate and the correlation variables with that predicate. So now we can have this much as the best optimized query for the nested one, because now we have converted the nested subquery into two simpler subqueries without having any correlation variables that join among this one. Not having the joining based on some predicates that we can have from the variables. So it is the best one to choose among this cost optimization on a nested subquery. Now we can rewrite our previous query or the original query as to the selection part of this and the creating table on a temporary basis like this one. So now rewrite this query as a resultant output to the optimized query on a nested subquery. So the first query we are having that we are creating a table T1 as select the distinct ID. So here the value is replaced with this ID that we can have from this teachers as from this L2. Now where the predicates that we are only using year equals to 2007, not the correlation variables that is teachers ID equals to instructor ID. Now we will use the second query as this one. Now we are having as the second query as this we are selecting name from the instructor and the table 1 that is T1 where the T1.id equals to instructor.id. That means we are having the predicate again with this correlation variable that is ID but not as a subquery but as a different query with simpler operation. Now, rewriting a simpler operation joining into the nested subquery is known as decorrelation. So, why decorrelation is needed? It is needed for the user designing purpose on a database, but for the performance on an evaluation engine, we need the correlation evaluation. So that is all for this today that we have discussed all the joined order, the heuristic search and the join order and heuristic plan caching. Then we have this one that the nested subquery evaluation on this memoization or dynamic programming construct. So now we can generate all the evaluation plans from these expressions and then choose the evaluation plan out of the least cost taking or the best effective one as our resultant plan. Thank you for watching this video. Stay tuned with Ekeeda and subscribe to Ekeeda.